this video, we're going to talk about a concept called Hess's Law. So in general, there are two ways that we can think about determining the amount of heat involved in a chemical change. The most straightforward, maybe, is to measure it experimentally, but it turns out we can also calculate it from other experimentally determined enthalpy changes. And so some reactions may be difficult, if not impossible, to investigate and accurately measure the energies produced. Even for reactions that are, it can be time-consuming, it can be expensive, and so it's very useful if we could calculate the heat involved in a chemical reaction by using other experimental data that we can tabulate and collect. And so what Hess's law tells us is that if a process can be written as the sum of several stepwise processes, then the enthalpy change of the total process equals the sum of the enthalpy changes of the various steps. And so that's sort of a fancy way of saying we're going to combine a bunch of reactions together to give us a new overall reaction, and then we can add up the enthalpies of the individual reactions to get the enthalpy of the new reaction. And part of the reason we made a big deal about the fact that enthalpy is a state function is because this is only possible if enthalpy is a state function. Because it doesn't matter whether we get from the reactants to the products in one step, or if we do it in a lot of different steps, as long as the beginning and end results are the same, the change in enthalpy is going to be the same. And that's only true for state functions. All right, let's kind of look at an example of what we're talking about. Right, so imagine we're interested in the heat involved in the conversion of, or the reaction of, solid carbon with oxygen gas to produce CO2. So we're interested in this overall process. Well, the delta H for that process is negative 394 kilojoules. But instead of doing it in one step, I could imagine doing this in two steps. So if I reacted the carbon with half a mole of oxygen to produce carbon monoxide, and then take that carbon monoxide and react that with half a mole of oxygen to produce CO2, if I add the enthalpies of these two steps together that give the overall reaction, the enthalpy is going to be the same. And when we think about adding reactions, right, it's kind of like what we did with spectator ions. If we have the same thing on both sides, we can cancel it out, right? So when I combine these two reactions, because I have CO as a product and CO as a reactant, I can imagine canceling those out. And I have two 1/2 O2s on the reactants. So when I add these reactions up, the CO's canceled, and so the reactants are going to be carbon solid, and then 1/2 O2 plus 1/2 O2 gives me 1 O2, and then I get CO2 gas on the products. So you can see that when I added these two reactions together, I got this new overall reaction, and when I add the enthalpies of these two steps, negative 111 plus negative 283, I get the delta H of the overall reaction is negative 394 kilojoules. All right, now there are some other relationships involving delta H and similar reactions that we want to talk about. So if a chemical reaction is multiplied by some factor, and usually it's going to be an integer, then to get the delta H for the new reaction, we just multiply it by the same factor. So I have the reaction, generic reaction here, A plus 2B goes to C. If I wanted to know the enthalpy for this reaction, which is exactly 3 times the first one, right? I multiplied A by 3, I multiplied B by 3, I multiplied C by 3, then our new delta H is just going to be 3 times the original delta H, right? I multiplied this reaction by 3 to get this new reaction, so I'll just do the same thing to the delta H's. So the delta H of this new reaction is going to be 3 times 153, and so it's going to be 459 kilojoules. All right, another thing that I can do to reactions is I can reverse them. And so the reaction that I have here is just the backwards form of this one, right? I just swapped the reactants and the products, and so now I'm converting 3C's into 3A plus 6B. When I do that, the only thing that changes is the sign on delta H. So delta H was positive for the first one, and so when I reverse that reaction, I'll have the same magnitude of delta H, but now it will become negative. All right, and we already saw in the last example that when I add reactions together, I add their enthalpies. So when I add these reactions, the C's would cancel, and so I end up with A plus 2B on the reactants, 2D on the products, and so to get my new delta H, I would just add the delta H's of the individual reactions. So I'd have 153 plus a negative is minus 200, and so I would have negative 47 kilojoules for that new reaction. All right, so what we'll do for the rest of the video is look at some examples of applying this to other chemical reactions. All right, so the way that these problems are typically presented to us is we're given a chemical reaction that we want to know the delta H for, and then we're given some related reactions where we know the delta H's. And so what we want to do is we want to combine these reactions together in such a way that it gives us this overall reaction. So it's kind of like putting together a puzzle, right? I need to either flip these around or multiply them by an integer or add them together so that when I combine them, I can cancel out the things that I don't want, and I'm left with the reactants and products that I do want. And so what I usually do is take each compound in the overall reaction one by one, find them in the reactions that I'm given, and then modify those reactions to get the compound on the proper side of the arrow, either the reactants or the products, and so that I have the correct number of them. And so I usually just start with the first reactant. And so I'm going to look for calcium oxide solid in my reactions down here. And so, right, that compound is not in the first reaction, but here it is in the second one, right? But when I compare that to this reaction, it's on the wrong side, and there's too many of them, right? So it's on the products here, and here it's on the reactants, and there's two of them, and I want just one. So what I'm going to do is I'm going to take this reaction and I'm going to reverse it. So I'm going to swap the reactants and the products, and that'll change the sign on the delta H. When I flip the reaction, it'll change from negative to positive, and then because I only want one calcium oxide instead of two, I'm going to multiply this whole reaction by 1/2. And so I'll do the same thing to the delta H. I'll multiply it by 1/2. So I'm going to flip it and multiply it by 1/2. So I'll change the sign and multiply it by 1/2. So that new reaction is going to be and then the delta H for this new reaction is going to be, I'm going to change this to a positive and then divide it by 2. And so that's going to give me 634.9 kilojoules. All right, and so now I would go to the CO2 gas. And so here's CO2 gas. This is the only place where I have CO2 gas in either of these reactions. And in this case, it's on the correct side, right? I want it to be a reactant, and it's a reactant. And I want one of them, and there's one of them. So I'm just going to leave this reaction alone. I'm not going to change it, so the delta H won't change. And so now I have and since I didn't change that reaction, its delta H won't change. And now I've used both of the reactions I was given, so if this doesn't work, then I've probably done something wrong. And so I want to see if there's anything I can cancel out. And so I've got a half O2 on the products in this reaction and a half O2 on the reactants in that reaction. So those will cancel. And then I have a calcium solid, 1 mole of calcium solid on the products in the first one, 1 mole of calcium solid on the reactants in the second one, and so that'll cancel out. I don't see anything else that cancels, and so now, right, I'll take all the reactants that I have left, and they'll be my new reactants, and then all the products will be, that are left will be the products, and so I'm left with and so that is the reaction I wanted. And so when I added these two reactions, with these delta H's, I got the reaction I wanted, so now I just need to add these two delta H's. And so 634.9 minus 812.8, and I get a delta H of negative 177.9 kilojoules. And so that would be our answer. Okay, here's one more reaction, and now I have three reactions to play with. So I want to, rearrange these reactions, flip them, multiply them by a constant or whatever, so that when I add them together, I'll get this overall reaction. And so again, I'll just start with the CS2 liquid, and so look for that in the reaction I'm given, and here it is. But again, it's on the wrong side. But I have the right number of them. I want 1 mole and I have 1 mole. It's just a product instead of reactant, and so I'm going to flip this reaction. So I have and so that delta H is now going to be negative 87.9 kilojoules. All right, and then I would go to the oxygen. Now, if you notice, the oxygen is a little bit tricky. So I have oxygen here and oxygen here. And so it's like, which one do I use? Or do I use both of them? When I encounter this situation, what I usually do is skip the oxygen, right? Figure out how to get the other compounds. And so I'd move to the products, and then the O2 will often work itself out. And so let's skip the oxygen, and we'll go to the CO2. And so I have CO2 is only here, and I have the correct number of moles, and it's on the products where I want it, and so I'll just leave this delta H alone. So I will rewrite it. I always rewrite them so I don't get confused about which ones I'm actually using. So now I have C solid plus O2 gas. CO2 gas. I didn't change that reaction, so I won't change the delta H. Okay, and then we'll go to the SO2. And so the only place I have SO2 is here, and now it's on the correct side. It's a product where I want it, but I only have one of them. I want 2 moles, so I'm going to multiply this whole reaction by 2, so I'll multiply that delta H by 2. So now I have 2 sulfur solid, 2 O2 gas, and then my new delta H will be the old one multiplied by 2, and for that I get negative 593.6. All right, and let's see, I've used all the reactions. Let's see now if when I add them together I get what I want. So the carbon solids cancel. I've got 2 sulfurs on the reactants here, 2 sulfurs on the products there, so those will cancel. I think that's all that cancels, and so now when I collect my reactants, I'm going to have, when I add these guys up, I have CS2 liquid. Right, and now these oxygens are on the same side, so they don't cancel, they're going to add together. And so I'm going to end up with 3 oxygens. And that's going to make CO2 plus 2 SO2. Right, and so by adding them together in this way, I got the reaction that I was looking for. And so now I just need to add the delta H's. Right, so negative 87.9 minus 393.5 minus 593.6, and my new delta H is negative 1075, and all of these have 1 decimal place, and so my final answer should have 1 decimal place because I'm adding, so that should be negative 1075.0 kilojoules. All right, and I've got another video with more examples of these if you want to take a look at that.